Clojure, a language presentation, presented by Brandon Gordon and Taylor Spinks.
So Clojure is based on lambda notation, which was created by Alonzo Church in about 1930. And the point of Church notation is everything is represented as a function. Following Church notation, a language at the time called Lisp was developed as a solution to a symbolic problem where they had to manipulate data objects as the program was running. And this is what brought about manipulated symbolic expressions, or S expressions. Clojure is a part of the Lisp dialect that runs on the JVM, which uses symbolic expressions to build data structures which you can manipulate as the program is operating.
Since its release in 2007, many prominent and highly popular companies such as Apple, eBay, Amazon, Netflix, and Spotify have begun using Clojure for their backend systems. Walmart's backend system, responsible for processing and integrating both online and physical sales at more than 5,000 stores, was redesigned in 2014 in preparation for Black Friday, with Clojure implemented all the way down. The new Clojure program encompasses 5 to 10 times less code than what previously existed, minimizing development and maintenance time, as well as reducing the chance of bugs. A developer responsible for writing and developing Clojure code at Netflix states that as of late 2018, it is still proactively being used within the Netflix infrastructure, namely for a querying service that handles approximately 2 trillion events a day for operational analysis. Being a functional language and a dialect of Lisp, Clojure enjoys the code as data philosophy, with a heavy focus on immutable data types and a concise yet powerful syntax. One major difference between Lisp dialects and other imperative-based languages is that syntax is not inherently text-based, more defined around the principle that data structures are the code. To assign the integer value 8 to x in Java, you would say int x equals 8. In Clojure, the comparable assignment statement is def x8. An important property of most Clojure expressions is that they are simply just a list containing an invoking symbol, in this case def, in the first element, known as the function position, directing the evaluation of the subsequent arguments. Just as def in the function position will define a new variable, placing an operator in the first element will direct the compiler to perform mathematical or logical evaluations. As shown in the examples to the right again, +1,5 will yield 6, dec x will yield the value in x decremented by 1, but the value of x will not change, and we'll talk about that in respects to immutability. Less than 2,4 will yield true, and similarly greater than 2,4 will yield false. An integral feature of Clojure's evaluation pipeline is the incorporation of the Java virtual machine. The traditional method will read Java source code documents in the form of .java files into the compiler as characters, producing bytecode to be executed by the JVM. Clojure's evaluation process differs in that the source code can come from one of two places, a .clj source code document or an interactive stream from the REPL, both of which are indiscriminately passed by the Clojure reader. The reader subsequently produces Clojure data structures which are read into the compiler to produce bytecode ready for the JVM to execute.
One of the issues with Clojure is that even though it's compiled, it's not actually compiled until it reaches the JVM layer. And at that layer is when it's pushed through a regular compiler process. But initially, Clojure actually passes through a reader. Now the reader is what breaks the expression down into an S expression. This adds 2 layers onto the process of converting Clojure into something that can be read by a computer. What's important with the reader in Clojure is that it can be accessed through the program. So if you have some source code and you want to modify a value of that S expression, that is accessible when you are actually running the program. Importantly with Clojure is that it converts, once it's been through the reader and once it's an S expression, that is then a data structure that is modifiable. Importantly, it's modifiable, but it's still immutable. So you can change elements, but you can't actually change the state of that data structure.
Clojure has very little limitations or conventions on how data is named within the source document. With that being said, in order for source documents to be efficiently and safely parsed and converted, some standards must still exist. Variable names have no fixed character limit and can contain alphanumeric and most special characters. However, they must begin with either a letter or an underscore. In an instance where a defined name contains multiple words, most modern languages have adopted the camel case notation as their standard. Clojure does not formally adopt this standard, instead opting for kebab case notation, whereby words are strung together using hyphens, as if the words are the tofu or vegetables and the hyphens are the skewers. As to be expected, names in Clojure are case sensitive, meaning that variable name with a capital V and a capital N will be referred to as a different data structure to variable name with no capitals. Although this has become quite commonly accepted within the programming community, some believe it to be a detriment to readability, with the view that similar looking names referring to different entities increases complexity when performing maintenance or review. Clojure's data types are inherited from Java. With that in mind, Clojure's data structures are immutable, meaning that a value cannot be changed in place, rather it must be recreated as a new value somewhere else. Integers can be represented as a decimal whole number, a short, a long, or an int, an octal number, a hexadecimal number, or a radix number. Numbers with fractional components can be represented by a floating point type, and true or false values can be represented with a boolean. Single characters can be represented by a char with the literal value defined via a prefix \, and with a chain of these characters represented by a string. Two varieties of the map data type exist within Clojure, hash maps and sorted maps, which function to associate some value with another value. Distinct from Java, however, is the atom data type, which taps into the functional paradigm of Clojure to provide a shared, synchronous, independent state that will never fall victim to race conditions and is used to represent changes which will be applied synchronously across multiple entities. As Clojure is a dialect of Lisp, many functional aspects of Clojure draw great inspiration from it. One such example being that binary operators within expressions are prefixed, meaning that they appear before the operands. Operator precedence is evaluated left to right and inside out. So to make sense of the example provided on screen, the inside bracket will be first evaluated to 18, and then the three resultant terms are added together, 3, 18, and 5, to reach an answer of 26. Many imperative languages have both statements performing some effect without returning a result, and expressions which do return a result. As much of Clojure's code relies on arguments being passed as parameters to a function, everything is an expression that can have some result evaluated from it. As previously discussed in relation to syntax, Clojure does not conform to the typical convention of utilizing the equal sign as the assignment operator. In fact, Clojure does not include the functionality of an assignment operator at all, instead opting to specify a definition in the function position of the list. The exclusion of an equal sign avoids the confusion of assignment with equality and creates a scenario whereby a single equal sign can be used in comparative statements, particularly useful for statement-level control structures as mentioned next. Within the Clojure language, control structures such as selection statements, iterative statements, recursion statements, and exception handling statements are natively possible. The if statement has a broad implementation within the language. The example shown on screen will output values are not equal, after evaluating whether the arguments following the equals symbol are equivalent, executing the immediately following line if the expression evaluates to true, or the line following that if the evaluation is false. The basic implementation of an if statement allows for only one expression to be executed for each branch of logic, hence the need for Clojure's if do statement, which allows for multiple expressions. The provided example outputs the values are both equal. Continuing with selection control statements, Clojure also includes functionality to implement multiple selection structures similar to the switch statement found in imperative languages. In Clojure, the case statement takes the form as shown on screen. This code example initializes the variable x to the value of 3, and then performs an evaluation to which a certain case of statements will be executed based on the result. In this case, the second case statement will execute. Iterative statement control structures exist within Clojure in the form of while, do-sec, do-times, and loop statements, each providing similar functionality, but each with unique attributes. Shown on screen, the while statement takes the following syntax, and works by first evaluating the Boolean expression and evaluating the statements while it yields true. Due to while loops performing evaluations on a value until it is no longer true, the value must be allowed to change, else the loop will execute infinitely. This becomes an issue when using data types in Clojure which are immutable. This is where the use of atoms, as defined by x with the value of 1 in this example, come in great use. The @ symbol before the x dereferences the value held by the atom, and the swap function replaces the existing value of x with inc, which will increment the existing value by 1, thus increasing the effective value of x each time the function is executed. Similar to a for each statement found in many other languages, the dosec structure is used to iterate over a sequence, such as a vector, and uses the syntax shown on screen. As the structure is iterated, the current value is stored in I, which can be then used in the body of the loop to make reference to it. A comparable statement in an imperative language such as Python looks relatively similar.
Subprograms refers to the ability to write programs that reference other programs within a program. So with Clojure, because it's a functional language, the ability to do this is core to that language. And this ultimately comes from the nature of a lambda expression. Because the lambda expression itself is a statement that has numerous functions. For example, see at the top, we're defining lambda x, lambda y, and then we're defining that y and x go together. This is to emulate that, as you can see in the Clojure example, if there was some library to handle strings, that you could combine those together in that way by doing a function definition. And then you see the equivalent in Python there, using a function definition with a function call and then passing an argument, which is the same sort of deal. It's just there's extra steps in there. You can also see that with Python, you have to actually assign it to memory, whereas in Clojure, you don't actually have to have a memory object because of the X expression stuff talked about in the lexical analysis.
Dating back to 1960 with the first release of COBOL, a record data structure was born, allowing the creation of a structure which could store named fields of different types under the one metaphorical roof. Clojure, being an advocate for simplicity and accessibility, does not include the modern functionality of methods to manipulate the data type's attributes, instead favoring the generic approach to information processing by keeping information in maps to be publicly accessible, just as it was for records in COBOL. Whilst this approach is still technically abstraction, the process of directly interacting with the record's map reduces the reliability and integrity of the data type, as it can be improperly manipulated outside of a safe range for that specific purpose. For example, a map entry containing the time in which a race driver completed their first lap might be 1:34:45, representing 1 minute, 34 seconds, and 45 milliseconds. However, as the map can be directly edited, there is nothing, strictly speaking, preventing the variable from being edited to 1:67:05, which does not make sense, as common logic will dictate that the seconds field should not exceed 60. To create a record and its constructor in Clojure, the keyword defRecord is used, followed by the proposed name of that record and the parameters it will receive. In this instance, driver being the name of the record, the three specified parameter names will become the keys for the record's map, and the specified values upon creation will be inserted in order. To create a new instance of that record, a variable of that type must be defined just as any other, beginning with def in the function position, followed by the name and associated values.
So encapsulation is a very popular construct in object-oriented languages, but in Clojure, it's not as straightforward as simply just declaring things as private or public or protected. See, Java uses those namespaces, and then you can use getters or accessors and setters and mutators to interact with the encapsulated objects. Now, with Clojure, the way to do this is by using a combination of swap with a hash. There are other ways to do this, but this is the example I'm using. And what this basically does is it says that this function in the brackets after the hash is an anonymous thing. We don't know what's inside it, but the swap actually inputs the C where the let C definition is, so that when you declare a C object, it will directly only access that increment C value. You cannot access any other part of that definition. As discussed in the report introduction, I talked a little bit about how just because a language is suited towards a particular paradigm doesn't mean that it is only that paradigm, which is the case in Clojure. There are lots of ways to suit different paradigms in Clojure for numerous different use cases. For example, you can see there that's an example of object orientation in Clojure, and the reason that works is because, as you can see, we have a person and an address object, and then we create an instance of that person and address object with some data, and then later on when we invoke that object, we can reference, say, the last name of Stu, and then we can get Stu's last name, which is Holloway. We also see that I've got a function definition of imperative. The reason Lisp dialect languages are imperative is because they have a specific order to them, such that you would do the define first, you would define hello first, and then you would do the next order of operations and the next order of operations. That would make the language itself imperative because there is a specific structure to it. As you can see, there's also an if statement, which means it's a structured procedural language as well, because we have a if statement, a declaration, and then we have flow control from there. Importantly, in Clojure, when doing concurrency or parallel processing or parallelism, data structures are immutable. So they are thread safe because they prevent other threads modifying those data structures when they are being used. That being said, there are ways to allocate things to different states of those data structures using references. Kind of similar in C, how you can use pointers to refer to addresses. References refer to a data structure or an instance of that data structure. There are different kinds of references to use in different circumstances. For example, refs or ref is used for synchronous change of multiple coordinated and synchronous change of multiple locations. What this means is that if you were to change something of that reference, or you were to change where that reference points to, in every other thread, that would be reflected. So that's synchronous, and also it means that coordinated because every other thread also reflects that change at the same time. Vars, they are a mutable storage location, so the storage location can be changed, and they're dynamically rebound per thread. So they can be while the program's running, they can be reallocated thread by thread. Agents is another aspect. They are mutable, but they independent and asynchronous, which means that if you change where an agent is pointing on that thread, that is only going to occur on that thread and at a different time to say that occurs on another thread. In other words, the threads don't really talk to each other about when that's going to occur. Atoms are importantly immutable. So once you declare an atom, you cannot change that later on. And they are synchronous, which means that they all can change at the same time, but in independent state, which means they only change per thread. There is no reflection of that on all the other threads. Parallel processing in Clojure is only supported through the JVM, which means it's supported, but you would probably do that through Java, not through Clojure, or you would run multiple instances of a Java program to do parallelism.
An exception can be defined as any unusual event, erroneous or not, that may require special processing, the likes of which aptly names exception handling. An event, whilst also requiring special processing, is triggered instead by external actions such as GUI interaction. Clojure implements exception handling off the back of Java, and as such includes similar syntax and functionality. The standard try-catch statement is shown on screen. Code which may prove problematic is placed within the protected code block, allowing the exception handler to catch the exception before it causes an issue, whilst recovering and informing the user of the problem. In the above code snippet, there is an attempt to read a string from a file, example.txt, and then print that string. Without exception handling, the program would crash if the file does not exist. However, when placed inside the bounds of an exception handler, the program can be allowed to recover from the exception, and the error is dealt with accordingly. An event handler, similar to an exception handler, is executed in response to the appearance of an event, as reported by event listeners. There is an example on screen which demonstrates the relative simplicity of event handling within Clojure.
Getting into Clojure is quite difficult because a lot of the concepts are very different from other languages. Because it's based in a Lisp dialect that is based from lambda calculus. And because they're not a usual thing that you would come across either in high school mathematics or even perhaps through university, it is very difficult to just go straight into Clojure and expect to know how to use it. You actually have to do all the prerequisite research before you can go ahead and use Clojure. For this reason, I would say in terms of readability and also writability, it's hard to get started with. But once you learn those foundations, once you understand the foundations, it's as easy as programming in any other language. Performance, unfortunately, when you go to run the reader on the JVM, there is a bit of a performance delay because the startup time means that you have to do the reading, convert it to an S expression or a data structure, and then it has to go through the compilation, and then it has to be going to the JVM, and then it has to be converted to machine code. So all of these features combined means that performance does suffer initially.
To wrap things up, Clojure is a functional language exploring some new ideas to keep it relevant in a modern programming environment. It is a dialect of Lisp, treating code as data and containing the Lisp macro system on the Java platform, advocating for immutable data structures to facilitate the growth of more robust and scalable programs, especially in a distributed environment. Running on the JVM, Clojure can maintain the positive aspects of a functional language whilst enjoying the rich collection of Java libraries, as well as a publishing platform with great reach. This accessibility can be attributed to the growing popularity that the language has experienced, with major companies adopting it to replace existing backend code with a functional language that can be incorporated easily into an existing architecture. As functional languages aren't commonly taught or adopted, many find the language difficult to initially begin creating something useful with. However, once the initial concepts of the language are understood, due to the relative simplicity of its syntax, code can be written in a fraction of the time compared to its imperative counterparts.
So question time. The question was, are there any aspects of the language that really would limit you using the language? I'd say first and foremost, the biggest inhibiting factor of Clojure being adopted by many companies or even individuals is the setup required to get a functioning Clojure environment and in picking a suitable editor to write your code in. There isn't, at the moment as it stands, any IDE which will just work from setup. You have to do a lot of configuring, a lot of installing, and this is a huge inhibiting factor for individuals to pick up the language. And one of the major aspects of Clojure is the REPL, which is again another hassle to set up. And the REPL is the read, evaluate, print loop, and this allows you to interact with the program that you're creating, and also it's where all the print outputs will be sent to. And most importantly, it needs to hook into a Java environment as well, which is again another hassle to set up and make sure it's working properly. Another major factor inhibiting the use of the language is the lack of learning resources available online. Since this is again such an infant language and it's not widely taught or adopted by many places, there isn't many sort of guides or tutorials as there would be for other languages such as C or Java. There's a lot of unusual things and a lot of things that aren't necessarily conveyed in many tutorials. There's a lot of presumed knowledge that you have background in maths or Lisp and stuff like that, when in reality most times you don't.
Question 3. Provide some interesting features of the language that sets it apart from similar languages. So when it comes to Clojure, it is a hosted language, which immediately is very different to most languages. Most languages just run on either a virtual machine like Java, or they run on their own little virtual machine like .NET, for example, C++, whereas Clojure runs on top of Java, on top of the JVM. Clojure also has great support for multi-threading. This is not common in a lot of languages because multi-threading is all about states. And if remember in the actual presentation, when we're talking about state, is that states can have identities, and those identities can change. So that means that you don't have to have mutex locks like you would in C, or locks like you would in Java, preventing access of a resource. So that's fantastic for Clojure, and that sets it apart. Another big one is that it's functional. Not many languages are purely functional. In fact, most of the languages that are purely functional are all based in the Lisp dialect. They're all dialects of Lisp. Another thing with Clojure is that it has excellent library support. You can condense Clojure down into a few lines for a lot of programs through the library support and through it being functional. An example of this would be the wall mount example that was used in the presentation.